Hi everyone. So we are on our fourth lesson, day one. So tomorrow we will have day two. And this is logging on. And we're going to keep logging on. We're going to solve logarithmic equations. So thus far we've been solving a lot of exponential equations, and now we're going to do the other one. And our learning targets for today is first, we're going to solve logarithmic equations arising from real world situations, and then solve for base, argument, and exponent of logarithmic equations. You ready for that? And then the next two we are going to do on tomorrow, next lesson. All right, so this is the do now. We are on page 207. So if you're in your book, you should be on page 207. And if you see right here, let me use this color right here. So these were the expressions that you were supposed to expand or condense. And if you notice, for the first two, you are expanding. So everything is in with one log. So what we're going to do is we're going to break it apart into like multiple logs. In these cases, only 2 or 3 logs, depending, right? So if you look right here, remember these are the properties that we did in previous lessons, log properties. And then I would maybe go to mad props. That's the one. 8 times x to the 4th. So we're just breaking up that 8 into x. And so it's going to be log base 3 of 8 plus 4 log base 3 of x. Remember that x right here. And then that 4, see if I can do this is right in front. Remember that exponent is going to go to the front because the exponent gets multiplied with the other exponent, which is the log, right? There we go. And let me just make this pink. We'll make this 8 right here. That's this 8 right there. See how they're all related? All right, same thing here. So we're basically, so there are 3 separate parts, the 5, the y, and the x. So what we're going to do is we're just going to break those into 3 different sections, okay? So this 5 right here is, so log base 2 of 5 right there. Now it's multiplying with the y. So then we're going to multiply it. So here's the y. So log base 2 of y. And what do we do with that exponent? We bring it to the front. So this y right here, that one right there. Okay, so that just goes to the front, just like that. And then, so here we say that is divided by x to the 4th. And if you notice, this x right here is on the bottom, so we signify that with doing a minus, and then here's the x, and remember to the 4th, so that 4 goes on front. Okay, so that's gonna be, let's make this color right here. So this 4 right here is in the one in front. All right, so hopefully those colors are helpful. All right, and we're gonna do the same thing here, except for number 3, we're going to condense it. So again, if you have not tried this before, pause me. So we're going to write this as 1 log, and then this is going to be x squared. So remember, we put that 2 up as the exponent, so that's x squared. And we know it's dividing, right? This is dividing because we have a minus right there. And then that's going to be divided by y squared on the bottom. All right. So now on to some real world things. Here are some pictures that I kind of took off the web. This is decibels. So basically a decibel is used by how loud a sound is, right? That's how we measure that. And this is the equation for that. So dB is decibels equals 10 times the log of I over IO. So I is the intensity of the sound, and IO is the intensity of the threshold sound. Okay, does that make sense? So what is the threshold sound? I always found this to be interesting. So basically the threshold sound is a sound that can barely be perceived. So like if you listen very carefully and it was really, really silent, and you might be able to hear this. You was like, it's like a little, little tiny sound, right? Whatever that sound is, whether it's a beep or someone's voice or a whistle, whatever, right? So it's barely perceivable. Okay, so that's going to be called the threshold sound. Anyways, what we're going to do is, the way we figure that out is we're going to basically find this proportion, right? How much intense a sound is compared to that barely audible sound. Okay, so the way so here we go. Anyways, so the sound in a quiet library is about 1,000 times as intense as a threshold sound. What? Is that not crazy or what? Right? Because I mean, a library is pretty quiet. If you look at the on the right here, this is actually the library in UW. you know. It's the reading room in Suzzallo Library that I don't hardly ever go to, because when you go in there, it's like, okay, it's really cool to be in there, but it's also like very quiet. And if you like even like open your zipper too loud, the people look at you and you're like, oh, sorry. So you're like slowly opening your zipper, trying to open it and get the book out. And you're like, you don't want to eat a candy bar. That's all I'm going to say. Bad days, right? A granola bar, yeah, no thank you. The crunch, everybody hears that. Or if your music is too loud, yeah, everybody hears that. You don't want that. And so, yeah, I usually don't go here. Every now and then you'll hear somebody snoring. Maybe that contributes to this 1,000 times intense, right? But anyways, so this place, great place to read or sleep, but read. So that's 1,000 times more intense. So here we go. You notice that I is equal to 1,000 times the intensity threshold, right? So how we want to get this proportion of I over IO, right? So what we're going to do is just divide both sides by IO, right? And then what do you get? I over IO is equal to 1,000, right? Because it's 1,000 times more intense. So what we're going to do is we're going to plug that into where this I over IO is. Do you see how I made them the same color? Yeah, same thing. So we're going to plug that in there. And then so you're going to get your calculator. Come on, calculator. And you're going to be like, okay, here's 10. And you don't need to put times because it automatically assumes that times log of 1,000. Notice we don't have any bases here, so we're just doing that. And then that's going to be 30. So there we go. So we have 30 right there. So the decibels is 30. And the reason why we use logs is because this intensity, if you can imagine, if a quiet library is like 1,000 times greater, and could you imagine, like, let's say what a very busy city street is going to sound like, right? Or a rock concert, or, you know, a screaming baby, okay, crying baby, but right, can you imagine, right? Those are going to be in really, really high. So the way we can kind of make these numbers more manageable is by using the log, right? So we're going to log these numbers and then see, and these numbers are much smaller to deal with, right? So easier to graph, easier to talk about. Can you imagine trying to make a graph that starts at, that we can, it goes all the way from like 1 to like 500 million, right? That you're not going to see all this stuff in the, is too small, right? That what units are you going to go by? So again, so the sound of traffic on a city street is calculated to be 500 million times as intense as the threshold sound. Calculate the decibel level for the city, for city traffic. So imagine, you know, cars going by, you know, maybe there's motorcycles, you know, trucks are stopping, delivering this whatever stuff. People are walking and talking and screaming or whatever it is, right? Running, all the different sounds in a city, which I haven't heard in a while, right? But so that's at that's 500 million times as intense as a threshold sound. So the I over IO is 500 million. It's really big. So literally, we're just going to substitute that in, put it in there, and what do you get? It is 87.0. Again, try this in your calculator, practice it. This is a good time to practice, just saying. And it's and again, so notice the number is not that big because logs can handle these big numbers, right? So it's 87 and some change, but it rounds to 87.0, which is same as 87, but this is to show that we did round to nearest 10th place. Why 10th place? Because it's decibels. We don't need like 4 decimal places. Okay, we're not trying to build a bridge here. We're just trying to figure out what are the decibels, right? And then this cute little baby, so cute. So the sound of a crying baby registers at 115 decibels. That is louder than a city street, just saying. So if you were at a city street and there was a baby crying there, you could probably hear the baby crying. This is why. And so if you take a look at this, inside the dB, we're going to put in the 115 right here. All right, and let me bring up my color so you can see. See, now you see my mouse pretty better. So that's where the 115 is, and then it's going to be 10 times the log of I over IO. And this is the I over IO is what we need. Do we need to know what I and the IO stand for? I mean, what numbers they are? No, we just want to know the proportion. Okay, so if you take a look, or the ratio. Anyways, so here we're dividing both sides by 10 because you have to. We want to change it to exponentials. We need just log by itself, no other numbers in the front. So we divide by 10 and we get 11.5 is equal to log of I over IO. And then we're going to notice a triangle, the triangle. So remember, if there's no base, it's base 10. And then I over IO, and then is equal to 11.5. So this right here, so I over IO is equal to 10 to the 11.5. And if you on your calculator, it's going to look like this. So we got 10 to the 11.5. And what do we get? This huge number, right? And you're like, maybe it doesn't look that huge because it's just 3.16. But remember, this is E. Think of E like exponent, right? I don't know if that's exactly what it stands for, but I just think of it like exponent. So that's going to be 10 to the 11th power, which means this, which means we're multiplying this small number of 3.1623 by a number that has 1 and 11 zeros. So in essence, we're just moving this decimal place over 11 times. So we would get about 316 billion times more intense than the intensity threshold. Just saying. So how much, just as my own personal question, how much louder is it than the city, right? Because we know the city is like 500 million. So we take this big, huge number and divide that by 500 million. I mean, which in and of itself is a big number. 1, 2, 3. Yeah, that's a lot of zeros. And what do you get? So the sound of a baby crying, right, at a loud, not whimpering, crying, right, is 632 times more intense than the city streets. Do you see how loud this is? And that's like it's a lot. All right. They know how to get attention. That's all I'm gonna say. Serious. Although kind of cute. But anyways, so and this one right here, it does talk about, we didn't talk about this in class, but it does talk about, you know, medication and like how do doctors know how much medicine is left in your body, right? Because it's kind of important when you're trying to figure out like dosage, right? And like what time you need to eat the medicine, right? And so that's going to be, this is the general equation of that. We're not going to get into this that much. We're just going to look at a worked example. So if you look here on page 210, there is a worked example there. So this is what I always like to do. I just look at it. And so there's this set up for us right here. So they put in all the information that they knew, and they just need to know their R, which is the rate. What is the approximate rate? And if you look here, if you go to the next step, there's like, this is not a fraction anymore, right? So which means they must have multiplied both sides by R times 1 minus, or R, oh my goodness, log of 1 minus R is what I was trying to say, right? And if you look right here, it says multiply both sides of the equation by log of 1 minus R. Yay. And so that's what they did. So I like to visually do that here, just writing it down. And then from here, all they do, put this in the calculator. I would not recommend that you do this on a calculator and then round it here. Okay, I would not recommend you round in general until you get to the end. Okay, so just keep this in your calculator. So I'll show you. We did not do this in class together, but I will just go log of 75 or so 0.75. There we go. Enter. So they got negative 0.125. That's their rounded estimate, right? And then what I would do is, so when you write it down, you'd have to do it that way. But, and then notice right here, they divide both sides by 4. So I'm just going to take this and divide that by 4, right? See how we go. And then, so now it's negative 0.03123. So do you see how it's a little bit different here? Because they rounded all the way from the beginning. And even if you do that, then I would go all the way to the end and then just round it at the very, very end. And then, so from here, what you're going to do is you're just going to solve for R. What I like to do is I like to add R to both sides. Oops, can't do that with a highlighter. So I'm going to add R to both sides. So then I would get R plus 10 to the negative 0.03125 is equal to 1. I like to do that to get rid of the negative R. And then I'm going to just subtract this right here, right? If I can do it, so hard. And then you get this right here. Okay, and then all you're going to do is, We didn't talk about anything. I'm like, how did we get from here to here then? Did you guys notice that? Did you, were you asking that question too? You're like, wait a minute, how'd you do that? And so if you notice right here, all of a sudden there's no logs. What happened? Right, we just changed to exponentials, okay? So that's gonna be 10 to the, so it'd be 10, we write down 10, because remember this is base 10, and then we write 1.1 minus r, and then on top is the answer of the log, it's right up here. So it's gonna be 10 to the negative 0.03125 is equal to 1 minus r. And then we do all that stuff. Okay, I'm sorry. And then we're gonna figure that out. So the way we would do this, I go 1 minus 10. Now remember, how do we get this previous answer? We just go exponent. And do you see that blue on, I think almost every calculator I've seen, I've always seen an ANS, right? That's going to be the answer of the previous answer. So the ANS represents this previous number, not 2 times ago or 3 times ago. It's just the most recent one. And we put answer, and there we go. And if you notice, right, 0.0694. There we go. Rounded at the end. It's a better way to go. Okie dokies. I mean, wouldn't you want your doctor to round that at the end instead of in the middle? Just saying. All right. So we're going to do some more problems of solving. There are, so far that we know, 2 ways of solving problems. You either run away from it. No, I'm just kidding. So here is the list all the different ways that where x could be. So here x, if you know, it's highlighted. X is the unknown, or the x is the argument. Okay. Here in the middle, the exponent is the unknown. So right here, that's called the exponent. Why? Because logs are exponents. And then the base here, see that little base right there? I highlighted it. That is the basis when the base is unknown. So there are 2 strategies, and one is more efficient than the other, let's just say. You can totally do both ways. They're totally completely legal. Just one takes a little bit shorter than the other one, okay? And it's a little less convoluted. But so the first way to do it is to rewrite as an exponential equation, which is what we've been doing, right? And then you're going to solve for x. And then the other way is to use the change of base formula and then solve for x. Either way, we're solving for x. End result should be the same. If it's not, we're in trouble. All right, something does not work then. And so if you notice right here, we just changed to exponentials, just like how we use the triangle of power. And then so x equal to 5 to the 3.1, which in your calculator, you put it in, and it's giving you about this, right? When we do it with the change of base formula, remember it's log of x over log of 5. That's the base goes on the bottom, right? And is equal to 3.1. And we have this log 5 on the bottom. So we're just going to multiply both sides by log 5. And if you notice right here, we get log of x is equal to log of 5. And we're just taking this 3.1 right here back to its exponent form right here, back as an exponent. And then we'll notice, well, if log of x is equal to log of 5 to the 3.1, well, then that x better equal 5 to the 3.1. If it doesn't, what's it doing? All right, so there we go. And we're like, ooh, this looks so familiar. Yeah, do it on your, we already did this one on our calculator. Exactly that, right? We got to that point in a little bit extra steps, but that's still fine, right? And so that's the answer you should have gotten. Which way is easier? That's up to you. But which way it requires less steps? The first way. So that's what we highlighted that one. So if you want to like put a bookmark or a little tabby thing, or fold your paper over a little bit because this will be a good reference to figure out which one should I use. Now, when your exponent is unknown, that's where you see the highlighted. You're going to try both ways. Change to exponents first, the exponential form. So 8 to the x is equal to 145. I'm like, well, what do you do here? If you remember, you can take the log on both sides, right? So we logged both sides. And remember, this exponent goes out to the front. And so we got 8 log x, log of 8 is equal to log of 145. And then the only thing we're going to do after that is just divide both sides by 8, or log 8. And then to get x is equal to log of 145 over the log of 8, which in your calculator It's going to give you 2.3933 about. And in general, when we have no context or whatever like that, we're going to round to 4 decimal places. That is 10 thousandths place. And then here on the right, we know, oh, I can just use the change of base formula. And so that's log of 145 over the log of 8. Notice both of those have logs on them, right? And then you put that in your calculator and you'll be like, oh, same thing. See how we skipped a couple of steps doing it this way? So yeah, the right way is definitely the better way, or easy, faster way to go, shall I say. Both ways are perfectly fine. And then the last one, again, so this is x to the 6.7, and that's equal to 24. How to get rid of an exponent in general? Do it to that root, right? So it's going to be 6.7th root. There we go. And in your calculator, you can do it one of two ways. So you can do it, if you have this, you're going to write 6.7 and then go math. And right here, do you see number 5 is the x root? And then put 24 inside there. And you get 1.6069, et cetera, right? Or if you want to, if you're like, I can't find that button, Miss Lee, what I do? So it's pretty easy. It's 24 to the, and if this was negative, I would make sure they put, parentheses around that. But this would be to the, now not to the 6.7 because that's completely different, but remember it's a radical. So it's going to be 1 divided by 6.7, right? Because like the square root is 1 over 2, right? It becomes a fraction. So either way, same. If you're using Desmos, you will need to put parentheses around the 1. Start the parentheses there so that the divide by 6.7 stays in the exponent. All right. And we're going to press enter. And what do you know? What? It's the same thing, just like what we said, right? So either way you want to do it is fine. It'll do the same thing. And then here is the change of base. And again, just like with the first problem up here, we're going to have to multiply both sides by log x because that's in the denominator. You don't want it in the denominator. So then all we have left is log of 24 is equal to, remember this 6.7 goes back up to the exponent. So it's going to be log of x to the 6.7. And so that means that 24 has to equal x to the 6.7. So again, we would do the 6.7th root, we'll get the same answer. So it looks like here that the exponential form way is the more efficient way to go. All right, so we're going to skip a couple of these. Okay, so now we're going to go to these problems. And if you notice, I've color coordinated these. So anything that is in equal, so it's not with the log, the x is not with the log. Like notice the b, d, and f. These are all going to be change of base, because everything over here on the left with the logs are constant. Okay, so we can just change them to change of base. Anything that has an x in everything else next in the log, whether it's in the base or the argument, doesn't matter. We're going to change those to exponentials. Okay, so that's how you know. All right. So letter A here. There we go. Letter A here. Again, we're going to change these to exponentials. These are color coordinated there. So here's our triangle. So it's going to be 4x plus 3. Remember, we're going counterclockwise fashion. And then 1/2. So this is going to be 4 to the 1/2 power is equal to x plus 3. And remember, to 1/2 power, that's like the square root, right? So this is the square root of 4 is equal to x plus 3. Well, how do we get rid of plus 3? Subtract 3. So we're just going to subtract 3 on both sides. And what is the square root of 4? Square root of 4 is 2. Minus 3 is equal to x. So in other words, x is going to equal -1. Just like that. Ta-da! All right, and then we're going to go with B. And again, if you've not done these before, then please pause, do them yourself, get as far as you can, and then press play. All right. Here we go. And then again, we're doing this in triangle. Oh, no, not triangle. This is change of base. Remember, these are green. That's the change of base because our x is over on the other side. So we're going to go log of 9 over log of 4.5 is equal to x minus 1, right? And the way we get rid of a -1 is a +1. So we're going to get log of 9 over log of 4.5, which is, oh, not equal to, +1 is equal to x. And in our calculators, we're going to go log of 9, end parentheses, please make sure you're closing out that parentheses, divided by log of 4.5. Please close it because we are going to add 1 to it. So +1. So your calculator knows how to do order of operations. So always keep that rule. And we get 2.4608. 2.4608. It's about where it's going to be at. All right. And if you look at for C, notice C right here, we change this to exponentials because our x is in the base. And so that's going to be x plus 2 to the third power is equal to 7.1. And remember, to get rid of a cube, you got to cube root it. Okay, and then the math is pretty much the same thing. And then you should get x is approximately equal to -0.0780, rounding 4 decimal places. And for D right here, again, change of base, just like this, is equal to 2 minus x. And what we're going to do, I was like, well, we're just going to change x and the logs together. Just because I'm lazy and like I don't want to write them all out. So basically we're adding x to both sides, right? And that's why we get the x on the left, right? And no x on the right. And then I'm going to subtract this whole log business here. So that's what we have, is subtract this whole log business over here on the right. All right. And then again, you're going to put that in your calculator and you will get this. And you don't need to put parentheses around here for when you put it in the calculator because it's going to understand to divide that first and then subtract. All right. When I say it, I mean the calculator. All right. For E, the only thing you need to know is what is the base, because we're changing to exponentials, right? Because our x is in the argument. So remember, the base is E, not 10, right? That's what it's natural log. So it is E and then x plus 4. And then on the top, it's going to be 3.8. And it's going to be e to the 3.8 is equal to x plus 4. Subtract 4 on both sides. And remember, on your calculator, you're looking for that e, which is right above the ln. Again, natural log, right? See how they're all related? So here's e to the 3.8 power. Got to tab out. It's going to be -4. Just like that. And so it's going to be 40.7012, right? Round that correctly. There we go. And then we're going to try this one. So again, this is the last one we're going to use change of base with. So this is going to be log of 12 over log of 11 is equal to x minus 7. I get rid of the -7. Add 7 on both sides. And so you're going to get, that's supposed to be a 7. And then so you're going to get log of 12 over log of 11 plus 7 is equal to x. So we'll get our calculator out. Log of 12, close it out, divided by log of 11 plus 7, 8.0363. So that's going to be, x is about 8.0363. Okay, that's supposed to be about. That does not look like a very good about. Probably because I have 2 things going on there. So x is about. There we go. Couple more to go. So let's take a look here. Again, our exponent is in, or our x is in the base. So we're going to use the triangle method. So that's going to be 1 minus x to the 14.7, and that's going to equal 8. All right. We've done these before. So we're going to do this really weird and crazy 14.7th power. whatever that is, right? And then, so that's all we're gonna have left, that's gonna cancel out the radical. So we're gonna have 1 minus x is equal to 14.7th root of 8. And then how do we get rid of this guy? If I add x to both sides, get x plus 14.7th root is equal to 1. And then I'm going to subtract this right here. This is why I like to do it in my head, because this is a lot of work to write it down. And so this can be x is not about, it's exactly equal to 1 minus 14.7th root of 8. So in our calculator, this is what it's going to look like. So 1 minus 14.7. And I'm going to go math. And then number 5. There we go. And then we're going to do the radicand of 8. So that's going to be negative 0.15. It can't be 19, right? So it's going to be actually rounded up to 20. So this is about, is it negative? Yes. Negative 0.1520. And we state the zeros to show that we have indeed rounded to 4 decimal places. That's just what it ends up being. So we're just going to do this last one over here. So this is going to be, again, the x is in the argument. So we're going to have to change this to exponential. So it's 10 to the 1.3 power is equal to 4 minus x. Okay. And then the only thing we're going to do, I'm just going to switch the x and the 10. So it's going to be x is equal to 4 minus 10 to the 1.3. Whatever that is. All right, so let's try that out. 4 minus 10 to the 1.3, which is going to be negative 15.9526. 15.9526, about there. Let's see if I got that right. Oh, there we go. And we have finally our last problem. Okay, do it step by step. Let's go pink on this one. So we did this one on the left-hand side. Remember, it does go into, what is it called? We change to exponentials, right? We do the triangle. And then we're going to just solve and make it to 0. And then we factor. Remember crisscross method? It's still a thing, right? Crisscross method. And then just remember that it has to multiply. The two numbers have to multiply to 16, but add up to 6. Add or subtract up to 6. Right? In this case, it's subtracting. So it's going to be negative 8 and 2 is going to be negative 6. We knew it was negative 8 because if it was a negative 2 instead of the negative 8, it had positive 6. We don't want that. We want negative 6. All right. And then remember, we set those two equal to each other. And those would be our answers. And, solve for x. And then, so what I just did from here was just make sure that we plug it back into the argument right here, because we got to make sure that that argument is always positive. It cannot be 0 or negative. It's not possible. All right. So here we go right here. So this is going to be 6. 6 to the 1 power is equal to x squared plus x, right? We changed to exponentials. Again, 6 to the 1 is just 6. And then what are we going to do? Subtract 6. So we want to set it equal to 0 so that we can use, and honestly, if you don't remember, that way you could always use quadratic formula. If you remember the quadratic formula, or you can look in your previous book and find the quadratic formula. So this is x squared plus x minus 6. Remember, we cannot combine any like terms. And then if you notice right here, we're going to just go, well, what two numbers multiply to x squared? Like x times x. And what two numbers multiply to 6? Well, there's 1 and 6, but they don't add or subtract to be x. So it's got to be 2 and 3, right? And so we know one of these two has to be negative because it says it's a negative 6. So, but we wanted to add up to positive, which means it's got to be negative 2. right? So x times 2, negative 2 is negative 2x. X times 3 is 3x. So what do we have here? Just x, just what we have. So again, in factored form, this is going to be x minus 2 times x plus 3 is equal to 0. And we're going straight across. Just like this, just like this. Okay, and then set both of them equal to 0. So x minus 2 is equal to 0 and x plus 3 is equal to 0. So therefore, how to solve this? 2 plus 2, right? So it's equal to 2. So if 2 minus 2 equals 0, and this one would have to be negative 3. Again, the only thing I would check in here is just to make sure. I know that 2 is never going to give me any negative numbers here, but I got to check that 3, negative 3, right? So that negative 3 squared plus negative 3. So negative 3 squared is negative 3 times negative 3, which is positive 9, plus negative 3, which is going to be 6. So we're good. If you want to check that for the other one, well, I already know that 2 is positive, and a positive squared is still positive, plus another positive is still positive. There's no way this is going to be negative. So there we go. So this is what your answer would be right here. All right. So get some practice in. If you have not already done the exit ticket, make sure you do that.